Hello everyone, I am Wang from Shanghai Jiao Tong University. It is my honor to share our recently published work. Firstly, I will introduce the background. To enable advanced multimedia services, 6G networks will need to deliver significantly higher data rates compared to 5G. Consequently, terahertz technology is essential to provide the necessary channel capacity and information transmission rates. The D-band emerges as a key candidate for future 6G wireless communication systems due to its abundant spectrum resources and low atmospheric attenuation. For modern electronic devices, miniaturization and integration are inevitable trends. Hardware solutions for consumer electronics are primarily realized through system-on-chip and system-in-package technologies. SoC integrates all components onto a single chip using semiconductor processes, while SiP assembles separately manufactured functional blocks into a single package. In recent years, IEEE fabrication methods have primarily fallen into three categories: LTCC, HDI, and wafer-level packaging. LTCC is the most popular IEEP solution, offering advantages such as stable high-frequency low-loss dielectrics, reliable thermal stability, and mechanical strength. However, beyond 100 GHz, LTCC faces challenges like layer-to-layer alignment inaccuracies and higher costs. HDI enables smaller vias and thinner traces but suffers from RF interconnection losses. WLP allows RF interconnections through vias and transmission lines, significantly reducing interconnect losses and improving overall system performance. However, popular fan-out WLP processes, such as EWLP, often impose design constraints on antennas, making it challenging to design a broadband antenna. We propose a broadband D-band antenna using WLP and heterogeneous integration. A metal cavity etched into high-resistivity silicon is filled with Rogers 5880, enhancing bandwidth and efficiency. A thin BCB interlayer supports the antenna, excited by a coupled feed method for adjustable frequency and matching. A parametric analysis is provided, with the results shown in this figure. The resonance frequency is closely related to the shunt capacitance C cavity, which is significantly influenced by the cavity dimensions. Increasing the cavity width shifts the resonance frequency lower, while reducing the cavity length also lowers the frequency. The feeding structure also significantly impacts antenna matching. Increasing the feed distance shifts the resonance frequency lower, while increasing the feed length shifts it higher. As can be seen, the coupled feed method provides design flexibility, mitigating parasitic effects and improving bandwidth. To highlight the advantages of our design, we compared the performance of the patch antenna under various scenarios. Our proposed design utilizes a metal back cavity and a coupled feed method to significantly enhance gain, bandwidth, and impedance matching. The MBC effectively mitigates beam deviation, ensuring stable and nearly identical broadside gains across a range of substrate thicknesses. The antenna was fabricated using a 9-step BCB process. A high-resistivity silicon wafer was prepared with silicon dioxide layers deposited on both sides. Cavity patterns were defined via photolithography and etching, followed by wet etching to create slopes for even silver paste coverage. A photoresist protected areas during dry etching, and trenches were formed using the Bosch process. A Rogers 5880 substrate and RFIC were embedded with silver paste, cured for smooth adhesion. Mechanical polishing enhanced flatness and interconnections, and the final WLP module was positioned in a PCB cavity for high performance. The proposed antenna element and array were measured through the quasi-in-air method. The single antenna and antenna array both have broadband performance. For the single antenna, the maximum simulated total and radiation efficiencies both reach approximately 95% at 136 GHz. The simulated average total efficiency is above 91% in the bandwidth. Compared to other D-band antennas, our design achieves wider bandwidth, lower profile, higher efficiency, and more stable gain, making it a strong candidate for future 6G systems. Thank you very much for your listening. I truly appreciate the opportunity to share our work with you. If you have any questions or would like to discuss further, please feel free to reach out. Your feedback and insights are highly valued. Thank you.